Good morning and welcome once again to Neutrino Day, Day 3. We are talking about matter mysteries in our universe. And today we are joined by Erica Caden, a scientist at SNOLAB. Erica is going to talk with us a little bit about the connections between SURF and SNOLAB. And there are a few, including Ray Davis, who was an experimental scientist here at SURF when it was still Homestake. And both labs have been involved very much in neutrino research. And Erica is going to talk to us a little bit about those connections. So welcome, Erica. How are you today?
I'm great. It's great to be here. Thank you for having me.
So glad to have you join us. Erica, can you just give us a quick overview of what you're going to do? And then I'll turn this over to you completely.
Yeah, sure. So I am going to, like you said, I'm a research scientist here at SNOLAB. I work on the neutrino experiments at the lab, and I am going to explain a little bit about how the questions that arose from the experiment that Ray Davis had when it was the Homestake mine were then solved in part by the SNO experiment, which then grew into SNOLAB up here in Sudbury, Ontario.
All right. Well, great. We'll let you get started. And folks, if you have any questions as the talk goes on, please submit them through a chat via Facebook or our website or any other platform you happen to be watching this on. Thank you.
All right. I'm going to share my screen and share my presentation that I've made. Okay, so again, here we are from neutrinos from Sanford Lab to SNOLAB. So particle physicists often start out with talks of giving a picture of the standard model. So this is a bit of a cuter version using the plushies available from the particlezoo.net. But this is pretty much a map of everything that we know about fundamental particles. So there are quarks that make up, they're protons and neutrons that make up our atoms, and there are leptons, which are more, which are fundamental particles. And at the very bottom here, you see the neutrinos, which are what I'll talk about today. But I like these stuffies for demonstration purposes, and they're just a nice way to show the particles in a more familiar way than just properties. What we also have here is the standard solar model. So this is all of the particles that are made from fusion in the sun. So the sun burns hydrogen and produces then helium and lithium and beryllium, and you can go down through much of the periodic table of the elements and see how these elements are made in stars. And what's interesting is that to particle physicists is that in this fusion process, neutrinos are given off at different points and in different energies. So what scientists, and especially what Ray Davis and an experimental physicist, and John Bacall, a theoretical physicist, wanted to do was use these neutrinos to study the model of the sun. If we can catch these neutrinos and look at their energies and look at their properties, we can confirm that this idea that we have about the sun is correct. So especially when we get so many neutrinos, this is the flux, how many neutrinos we get coming from the sun is 10 to the 11 per square centimeter, so about the size of your thumbnail per second. So this is a 1 with 11 zeros after it through your thumbnail every single second is how many neutrinos we are getting from the sun here on Earth. So this huge number of neutrinos meant that we thought it would be somewhat easy to catch them, to understand, to confirm our model of the sun by catching these neutrinos. So the idea that Ray Davis had was to build a giant vat of this carbon chloride, which is the material used in dry cleaning, to catch these neutrinos. So one isotope of chlorine 37, if a neutrino hits it, it turns into an atom of argon-37, and you can catch this single argon atom out of all of these chlorine atoms in this giant vat, this tank, 378 tons of the carbon chlorine. So about 25% of natural chlorine is the one isotope you want. So that's a pretty good enrichment already. So Ray Davis was sure that he knew how to build this experiment, look for the chlorine atoms, and John Bacall was sure that he understood how sun worked. So you just need to count the chlorine atoms that are converted from these neutrinos. It was basically looking for a needle in a haystack, because while neutrinos, we do have this huge number of neutrinos coming from the sun, they don't interact very strongly. They interact very rarely and only through one of the four fundamental forces that we know in nature. So you're really just looking for a handful of argon atoms every week or so from this huge tank. But we thought we could do it. But the problem was that Ray Davis only detected about a third of the amount of the neutrinos that John Bacall predicted. So you have this, what we call the electron type neutrino. So there's actually, I should have mentioned, there are 3 different flavors of neutrinos here. So this reaction was sensitive just to the electron type of neutrino. So Davis only detected a third of the amount of neutrinos that Bacall had predicted. So does that mean that we don't actually know how to count these chlorine atoms, that we don't know what is happening? We don't know how to build experiments? Or do the theorists not actually know what's happening in the sun? So they refine the experiment, they redo the calculations, they try again, and they're still not getting the right number of neutrinos from what is predicted to what the experiment actually showed. And this is not just in the chlorine experiment. There are other experiments looking at neutrinos produced in the atmosphere, interacting with water, and solar neutrinos interacting on an element called gallium, in addition to the chlorine. And nobody was getting the right number of predicted neutrinos compared to, they weren't counting the right number. They weren't measuring what was really happening. So are our predictions wrong or our experiments wrong? And this persisted for a couple of decades. 20 or 30 years, nobody was counting the right number of neutrinos compared to the predictions. And this was for all of the neutrinos that were predicted to be coming from the sun. So this really, really flummoxed scientists for a long time. Is the sun burning up? Are we a lot closer to the sun exploding? If this why we're not getting as many neutrinos as we think is, or do we just not understand anything that's going on? So as experimentalists and the theorists, everyone was puzzled. So then comes the SNO experiment to try and solve the problem that was first found by the homestake experiment in what is now SURF. So the SNO experiment was a kiloton of heavy water. So heavy water is normal water is hydrogen and oxygen. We know this. If you have hydrogen is just a proton in its nucleus, but if you have, so a proton being a red plushie, but if you have a neutron in the nucleus as well, you still have hydrogen, but it's a heavier hydrogen. So water made with this heavier hydrogen, or the deuteron, is called heavy water. And it's what's used in the nuclear reactors in Canada to cool them, different than the nuclear reactors in most other parts of the world. So Canada had this huge this vast reserves of heavy water. So the SNO experiment used heavy water as its target material. Its location was 2 kilometers underground in an active mine, in a locally owned mine called Inco. And they had incredible cleanliness constraints. So this detector, this is the outside of it. The picture that you see behind me is a picture of the inside of it. It's 18 meters across here. A huge, huge experiment with incredible cleanliness constraints. The amount of dust that was allowed to have settled after building this inside an active mine, and mines are not very clean places, the amount of dust could have fit on a quarter. It was so, so clean. And this was needed to try to measure these different reactions. So the reactions that SNO measured were different than any of the ways to measure neutrinos from the previous experiments because they had this heavy water. So the electron neutrinos that were produced in the sun could convert the neutron in this heavy water atom into a proton and produce an electron that would make this pretty circle, a Cherenkov ring inside the detector. But we know that there were two other reactions that were sensitive to all of the three different flavors of neutrinos, that you could just break apart the heavy water nucleus, so you have a free neutron hanging out, and you can see that interacting in your detector, or you could have elastic scattering. And this was also something that all three different neutrino flavors could do. And you would just, the neutrino would bounce off an electron, and this electron would then produce that pretty ring. So three different reactions that were visible in three different ways in the detector. Some were only available to this electron type neutrino that is produced in the sun, and three were, or two were available to any of the neutrino flavors that we had learned about at this point in time. So we could then test what is happening in the sun in a different way that the other experiments were. So this was one of the great successes of SNO, is that it confirmed the electron results that the chlorine experiments did. So they have this result that, yes, when you're only looking at the electron neutrinos that are coming from the sun, you only get about a third of what is predicted. But if you look for all kinds of neutrino interactions, if neutrinos are changing what flavor, as we call them, they are as they're traveling from the sun to the earth, if you can count all of the different types of neutrinos, then you get the predicted number. Then you know that you're counting all of them. So this was the great success of the SNO experiment, that without having to, without having to know very well the model of what's happening in the sun, we were able to collect and count properly all of the neutrino interactions with just one detector too. So
Erica,
here are some pictures. So this is a scientist who was inside the detector. So it's filled with this heavy water, and we use these boats to lower down to check on the acrylic, the vessel. Each of these dots is one of our light sensors. They're called photomultiplier tubes. They're very sensitive light sensors. Here is a picture of that ring, the Cherenkov ring from one of the events. And here are the scientific results. So and how well the reactions, from the three different reactions, the electric scattering, the charge current that was only available to the electron neutrinos, and the neutral current, added all together, they matched very well with the data. And
Erica?
so this, hi.
Hi, I've got some questions here.
Oh, yes.
I was trying to get you earlier, but we had a little technical difficulty. Can you talk a little bit about the strange spherical shape of the detector?
Yes. So the detector is a sphere, and spheres are very common shapes for these detectors. Often you'll have cylinders or spheres for this type of detector. And it's made of acrylic. So the acrylic is 2 inches thick, and the whole detector is, I'm going to confuse units, I'm sorry. The whole detector is 12 meters in diameter. So I think that's something like 40 feet, with just 2-inch thick acrylic, as these walls that's holding this heavy water. So it is this fisheye lens is maybe a little distorted in the picture, but it's a big sphere filled with water, and being instrumented all over means that we can see light produced by these reactions from everywhere inside the detector. And it kind of makes all of the reconstruction and understanding where the event happened based on the light a little bit easier.
Okay, and then I have another question here. In heavy water, do both of the hydrogen atoms have a neutron?
I believe so.
Okay.
I'm not sure on that, actually.
Okay, so we need to do some research, right?
I believe so. I believe
All
so,
right.
yes.
Thank you.
Okay, thank you. That's a great question. So combining the results from the snow from 3 different reactions and the fact that they all meet at this one point in the middle was one of the great strengths. And this shows that we are properly counting the electron type of neutrinos. That Ray Davis was right, that the experiment that started the SURF lab was a successful experiment. It just didn't have all of the information. We didn't know at the time that neutrinos were changing what flavor they are as they're traveling through space. This isn't something that any of the other particles in the standard model, this beautiful model that I showed, none of the other particles do that to such a degree that neutrinos do. Most particles, they have a mass and they have their flavor properties, and they just stay what an up quark basically stays an up quark. But an electron type neutrino will change into a muon type neutrino to a tau type neutrino as it travels through space, back and forth and back and forth and back and forth, which is just a unique property of neutrinos. So based on the results from SNO and then understanding the results from the Super K experiments, both of these results came out in the 1990s. They really solidified, neutrinos oscillate. So what we know about neutrinos now is that they are their quantum properties, that we call them spin 1/2, but they're electrically neutral. So they don't have a charge. They barely interact with anything, and they only interact via the weak force. We have 3 different flavors of neutrinos that can oscillate from one kind to another. So a tau or a muon neutrino that is produced, say, in the accelerator at Fermilab can travel into either an electron or tau neutrino by the time it will hit detectors that are being built at SURF. And neutrinos are the most abundant massive particles in the universe. So we have more photons, but photons we know don't have any mass. So neutrinos are just everywhere. Like I said, 10 to the 11 pass through your thumb every second. And maybe one will interact in your body in your lifetime. That is how rare their interactions are for how many are streaming through us. So this is the layout inside of the lab for the SNO experiment. This was as people came down 2 kilometers underground every day and then walked another 1.5 kilometers to get to the experiment. They would come through these doors, and there were showers in a lunchroom here because you have to shower off to wash all of the dust from the mine off of you. And here is where the experiment was constructed. And here was the storage tanks and processing plant for the SNO experiment. So once the global science community realized what an amazing setup we had in Canada to create this experiment, it developed from SNO into all of SNOLAB. So now the lab has expanded into a whole facility holding 10, at the moment, I believe 10 current experiments studying not only neutrinos, but also looking for dark matter and doing some innovative biology that is only able to be done at SNOLAB due to its unique depth and cleanliness. So this is going from SNO to SNOLAB. So here is a picture of the surface building right now, which is, of course, kind of empty. Again, I wish I could be there with you. But this is from Lead. It would be about 24 hours of straight driving to get to Sudbury, Ontario. We are in an active mine, so there is still mining going on in uh, in Creighton Mine, which is now owned by Vale, one of our sponsors of the lab. So we go down again 6,800 feet, just over 2 kilometers, and then walk another 1.5 kilometers to get to the lab. So this red is the ore body. So we are a nickel mine, one of the largest nickel mines, or the Sudbury Basin has one of the largest nickel loads on the planet. And there is much more mining to go. They just keep going deeper and keep finding more and purer nickel. So this is very good for now the scientists that want to keep our area of the mine carved out. We are an international facility. We have over 850 users of the facilities here, from 130 institutes across 23 countries. So we are well represented, the world is well represented here at SNOLAB. Here is a beautiful picture I love of the entrance. So this was the old entrance. These had been the doors that opened into the lab. This was the area where pieces would be cleaned before they come in through. This door on the left is where people would walk through before they would go to shower and then go to the work. So now this is just in the middle of the lab. You can see the train tracks where materials were carted in. I just think this is a great, big welcoming perspective. So currently at the lab, we have these, in pink are the facilities, the part of the services that the lab provides to all of the experiments. In the blue are all of the current experiments. So like the biology and repair and flame, different process plants for the Snow Plus experiment. HALO is a supernova detector, and we have many dark matter experiments, NEWS-G, D3600, DAMIC, Super CDMS, PICO, and then future planned experiments, more dark matter experiments, Sensei, SBC, the next generation of the PICO experiment, and hopefully a ton scale double beta decay experiment, which would go in the cryo pit, which is the last unfilled cavern. This is waiting for more science. So here are, again, this plushies because I can't get enough of them. So SNOLAB's vision is to be an internationally recognized laboratory and partner of choice for deep underground science. And so we deliver world-class research and scientific discovery and benefit to Canada and her global partners, again, being an international facility, by enabling national and international access to our unique capabilities. One of the main things that we do at SNOLAB, or one of the large things that we do, is low background counting, which I believe you guys do too. We have counters to see what is the radioactivity of the materials that will be used to make our experiments. And being, again, so deep and so clean, we can provide very precise measurements of this. So to find out more about SNOLAB, we are on Facebook, Instagram, and Twitter at SNOLAB Science. And I look forward to answering more of your questions about everything.
Do we have more questions? Well, I have a question for you, Erica. Which experiment do you work on?
So I primarily work on Snow Plus, which is the one behind me. And I contribute to HALO. And I'm also working on Nexo, which is one of the future double beta decay experiments that would like to be in the cryo pit. So I stay primarily on the neutrino side more than the dark matter side.
Okay. Do we have any other questions from? Okay. Well, we don't have any other questions for you, Erica, but is there anything you'd like to add that maybe we didn't touch on?
I can take you guys on a bit of a tour of the lab.
Well, we would love that.
So we have a virtual reality setup that I will try to share screen for again. So if you go to snolab.ca, you can find our virtual reality tour, and we can kind of walk through everything. So this is what is now the car wash. This is how every material enters the lab. Um, every single piece that you see in the lab is cleaned here. So every bolt, every cable, every piece of equipment, every single item in the lab is cleaned here before it can go into the lab. So whenever you are sending an experiment, you also have to send people to help build the experiment, and especially people to help clean the pieces before they go in. We can say this is our refuge. So in any mine, you need the refuge to come and stay for safety. And ours, this is ours here. It also doubles as our lunchroom.
How many people can that hold?
I think by regulations, 125.
Okay.
It would be a little bit crowded, especially right now. But that's the limits for safety.
Okay.
So this is where everyone gathers in the morning, and then in the afternoon as things are leaving. So here is just on top of the SNOplus detector, and we can actually go inside the vessel. So this was during the refurbishment. So the SNO experiment ended in 2006 after they had collected all of their data, and all of the heavy water was drained and returned to Atomic Energy Canada. So it was just on loan. They didn't buy the heavy water. This is, I think, purchasing it would have been prohibitively expensive. So it was loaned, which was amazing. And so then the inside of the vessel was cleaned. Any of all of the photosensors here that you see that had broken were removed and refurbished and reinstalled. The SNO detector, so heavy water is obviously, maybe not obviously, it is heavier than regular water by about 10%. So the detector had to be held up by these ropes that you see in these grooves here. But right now, the SNOplus detector, which is a multi-purpose detector that is filled with a mineral oil-like substance called linearalkylbenzene. But it's essentially a mineral oil, but we know that oil is lighter than water. So the detector would float up if it wasn't anchored down by this rope net that you see here that was drilled into the floor. And this is another scientist, Ian Lawson. So we can now go underneath the floor, and these ropes were anchored down 10 meters into the rock to anchor the detector so it doesn't float up. So that was one of the refurbishments that was needed to go from the SNO experiment to the SNOplus experiment. So SNOplus is also looking for neutrinoless double beta decay, as well as neutrinos from the sun, neutrinos from nuclear reactors in southern Ontario, neutrinos from the Earth, so trying to study the Earth with neutrinos, as well as other exotic decays. So a very multi-purpose experiment.
Erica, as we've gone through this, a little bit of this virtual tour, I've gotten a couple of other questions.
Awesome.
What are the challenges of doing science in a working mine? And then are there any advantages, such as sharing excavation equipment or other mine-specific tools?
Yeah, so those are both great questions. So it's easy to say that some of the difficulties are also some of the advantages. Because it's a working mine, we have the mine company handles all of the water and the air and getting it to us, and runs the elevator, we call it the cage. So that is a huge advantage that we as scientists and the engineers at SNOLAB don't have to figure out and maintain that infrastructure. But like I said before, it's also very dirty and loud, and we are beholden to the mine schedule, which I think is also a good thing. There's specific hours. Scientists can sometimes overwork ourselves, so we're only allowed certain hours in the lab based on safety regulations. So I think that's a good thing. The dust and the dirt is probably the most difficult thing of working in an active mine. Sure. But you would have that in a non-active mine also, just maintaining the levels of cleanliness. And certainly when the lab was expanded from just the snow area into the entirety of SNOLAB, that made having the excavation equipment there made that possible and not easy, but almost easy.
Okay, thank you.
Yeah, that's a great question. So I can move. Let's see here. Oh no, well, we can check out HALO, which is another neutrino detector. So HALO is waiting for a supernova to happen in our within, I believe, 5 kiloparsec. So the neutrinos that are produced from a supernova will come and interact in the lead and produce neutrons that will be captured in their neutron counters. And by tying in this signal with other neutrino detectors around the world, we will be able to hopefully point our telescopes to see the supernova happening, like, as it's happening, instead of just the remnants, which is all we have seen so far. So having many neutrino detectors that are sensitive to supernova all tied in together around the globe is very exciting, especially now in these days, this era of multi-messenger astronomy, when so many different cosmological and galactic signals are the detectors are tied together, and we can see and confirm these signals in many different wavelength bands.
Erica,
Yeah.
I've got one more question. You talked about using lead to look for certain things. How do scientists determine that a certain material is going to be the most effective to find these mysterious particles or rare events?
So that's a good question. We have studied some of the reactions we know from the theory, what these reactions will be and how they will be most easily detected. So we know that a neutrino interacting with lead will produce a different signal than, say, than something else. So it comes from theory, and then we build small experiments, often to test out our ideas. We think that something should happen a certain way. So the research and development in detector technology, we'll start with a small experiment and then grow into a bigger experiment. So one of the experiments that I'll show you is, let's go to, this is taken after it was already closed up. The DEEP experiment is a dark matter detector that is here at SNOLAB that started as just DEEP one, a very small amount of liquid argon, and we're looking for a dark matter particle to bounce off the nucleus of an argon atom and produce some light. So there was a small test detector that was built and then expanded into a larger vessel with more mass. So the staging process. Another successful implementation of that has been the PICO detector, which started with 2 liters and then went up to 60 liters and then changed their design. So they went down to 40 liters and now is planning for 500 liters. So we have our ideas and we build small detectors to test that our ideas work and to kind of refine the process and make sure we have the right technology. And then we build larger detectors once we know we have it right, that are more sensitive to what we're looking for.
Erica,
that's a great question.
I have another question for you. This is from one of our speakers coming up. He wants to know, who is your favorite guest who has ever visited SNOLAB?
Personally, I'll have to say my mom.
Oh, excellent.
Bringing my mom underground and getting to show her what I do, that was really exciting. But I love bringing people underground. I love showing around the lab what we have done already and what we are planning to do. So this is where we are now in the map is an area called the cryo pit, which is the last unfilled cavern. And for now, it's here a bit of storage area, but this is where the next double beta decay experiment will be hosted. And so what can be done here. So this is now looking down. This is what I like to show, where science is going. But I very much enjoy giving tours of the lab and look forward to a time again when we are able to do such things.
Looks great. Do we have another question coming in? Okay, we do have one. Okay. Does the nickel lode in the mine present concerns related to detection, like background or anything like that?
So the nickel itself, it doesn't produce any issues, but the general rock dust does. So rock, as any rock anywhere, has a decent amount of uranium and thorium in it, as well as other materials, other elements. But the uranium and thorium have some pretty long-lived backgrounds that if they get into our detectors, they would produce small signals forever that would diminish our ability to look for the signals that we're searching for, to look for the light that's produced by neutrinos or by dark matter interacting in our detectors. So this is why we have to be so clean, why we have to make sure we wash all the dust off of ourselves. You have to wash your hair every time you go into work underground, and you have to clean all of the materials that the detectors are made of. So this is, again, cleaning on the outside, as in the car wash, one of the first pictures I showed, but also making sure that the materials themselves are clean. So using our low background counters to make sure that there's not extra radioactivity in, say, the acrylic or in the photomultiplier tubes or in any of the other materials that our detectors are made of, so that they don't blind ourselves to the signals that we're trying to see.
Okay. And we have another question here. What is the process used to determine which new experiments should be brought to SNOLAB?
So there is an advisory committee. So if you want to have your experiment at SNOLAB, you can write a letter of interest, and the scientific committees will kind of evaluate it and see if your scientific goals align with the scientific goals of the lab. If it's possible to be done in a safe manner, safe to people, safe to the environment, and safe to all of the other experiments. And then you would go through a development process. But I would say good luck, because we're just about full of experiments. With this last cavern kind of dedicated to the next neutrinoless double beta decay experiment. We're kind of all out of space for big experiments. If you have, a small prototype, that could be a possibility. But even in some of that, we're running out of corners to put these small experiments, which is kind of sad, but also very exciting that this facility has grown into what it was envisioned to be full of all of the projects.
Great, thank you. So we have no more questions? Is there anything else you'd like to bring up, Erica?
I would say just, again, follow us on @SNOLAB Science on all of the social media channels. The Instagram is especially alive with Monday astronomy pictures and Friday faces. It's amazing how many pieces of equipment in the lab you can see faces in them. So that's one of our favorite things that we've been sharing during this time. We have a seminar series over the summer, and just getting more information about the experiments that are going on in construction and that are currently running now. So yeah, at SNOLAB Science.
Well, thank you so much, Erica. It's been great talking with you and having this connection to SNOLAB. So I'd like to just remind people to stay tuned for the neutrino discussion at 10 a.m. Mountain Time with dune scientist Ryan Patterson and science comedian Brian Mallow. That's coming up in just a few minutes. Thank you.
Thank you.